being null has one of two different meanings. It could mean your tree is empty. It could mean the data you're looking for is not a match. Only the wrapper function knows. So in the wrapper function, if root's null, you have an empty tree. Why did you even call the recursive function? Okay? And then you go into your recursive remove until you find your match. Please, you are not going to want to go and call a retrieve function and unwind the stack and then call another function to find it, okay? So this is not a retrieve. This is taking you down to a match, and then we're going to start working from that point forward. Okay? So your removal needs to travel the tree for a match. All right, so first empty, 2 is no match. So now we have a match. Yay, we have a match. Woohoo! Sorry. So 40 is our match. Whoa, we found it, yes. Okay, I know, so I'm sorry. So case 3 is, it's a leaf. How do I know if something is a leaf? Its 2 children are null. So my left pointer and my right pointer are null. Well, okay, so what do you do recursively if you're doing a linear linked list and you remove at the end? So your pointer is at null. You're pointing at the last node right now. So currents next is null. Or heads next is null. What do you do to remove it? So you set. Okay. Do I need a temporary pointer? All I have to do is say delete head, and head gets the value null. So let's draw that. So delete root. And if root was passed by reference, setting root to null, well, and again, this is just the overview. I have this all written down. Setting root to null will cause 35's right in this case to be beautifully null. The power of pass by reference, so delightful. Wherever I came from, I don't have to micromanage that. Okay? So a leaf. My children are null. Delete the node, set root to null. Done. No temporaries needed. Okay. Well, what if it wasn't a leaf? Next easiest is we have one child. So for example, not a very good tree. Let's say our match is 80. 80's left is null, but 80's right is not null. I have one child. This is like deleting in the middle of a linear linked list. Now we need a temporary holding on while we delete and we reset head. So exactly like that. So if on our stack frame root is an alias for where we came from, we can say temp gets the value root, root gets the value root arrow, root gets the value root arrow. How do I point around 80? Right. Delete the memory at temp. Deleting a node in the middle of a linear linked list. Hold, delete, hold, delete, reconnect properly. Don't access memory that you deleted. Be careful about that. But you've learned how to do this already. And you've learned how to do this recursively. You can do it. Let's try it again with 50. See if it works there. So 50s are matched, so my recursive call made root be an alias to its parents left. Root arrow data is the match. So temp gets the value root. Right? Can I do that? Can I say temp gets the value root? And root is a pointer to 50. That's why I put my temp as a pointer to 50. Update root. Root gets a value root arrow. Right. All right, maybe I draw it weird. Would you like that better? Delete temp. And 65 now points to the left to 55, and that's correct. So there is a special case here. I need to know if my parent, I need to know if my child is to the left or the right. So in these two cases, the child is to the right. So 90 was to the right, 55 was to the right. But what if I wanted to delete 90 and it had 85 to the left of it? So it's still deleting a node with one piece of data. I can hold on to this, readjust, but in this case I would be saying root gets a value root arrow left. Because the one child I'm holding on to is the left side. So that, again, I will go through all of this in more detail. This is still the overview. But the idea is I can't do that in the same code, sadly. Can I start combining some of these? Oh yeah, I can make messy code. I recommend each of these separate until you feel really confident about it before you start trying to clean up your code and combine anything. So is my one child to the left or is my one child to the right? That's going to be different code. We call this a name. This is called your parent is going to adopt your child. It's the adoption process. Your parent is willing to adopt one child. They have room for one child. No more. They just need to know, are we adopting the left one or are we adopting the right one? That's it. All right, so we'll just make a notation that we had different cases for the left versus the right. Case number 5. Uh-oh. I told you there were a lot of cases. They're all pretty small. Most of these are like 3 lines of code until now. Well, you implement these and you feel good about them. But what if I have 2 children? Okay? So let's say my match was 70. What if my match was 70? So I want to delete 70. And 50 says, I am not going to adopt 65 and 80. I mean, how could it? It couldn't, right? I mean, where would it put them? You'd have to do some creative things. Is it possible? Yes, you'd have to figure it out. and keep it within the rules of a binary search tree. So, the algorithm that we are about to learn in this overview is if you have two children, what you want to find is this thing called the in order successor. It's a very important term for data structures. I have like about 50 proficiency demo questions on in order successor. Hopefully I spelled it right. And 202, I probably have 100 questions on in order successor stuff. So this is not going away. So in order successor, let's dissect that. In order, what does that mean to you? Yeah, small to big. So in order. That's another word for in order. Successor. What's the word successor mean to you? You're the person that takes your job. They're the successor. You know, who's going to be king next, right? That's a successor. Who's going to take the Iron Throne? No, anyway. I don't know what that is. They have troubles. So, successor means who's going to take over for me, and I want it to be the next one in line, right? So it should be Jon Snow, sorry, because he's the next in line. No? All right, well anyway. So if I want to delete 70, look at this tree and tell me who's the next in line. 80, 100%, 80 is the next in line. 80 is the in-order successor. And the reason it's the in-order successor is it's the next in line. If you look from small to big, so it's the iOS, is what it's called, in-order successor. Sorry, Apple. It's the in-order successor because it has no left children. It's actually not the in-order successor because it's the right child. So, $80 is like Daenerys. No. But what if it had a left child, which is the next in order? Take 70, that's what we're trying to remove, which is the next in order. Next. 65's gone. No, they already got killed. No, sorry. 75. 75 here is what we call the in-order successor, or iOS. That is Jon Snow right there. So what we do, again, this is the overview. Thank goodness. We're going to move 75 up to its rightful throne. Oh, sorry. Okay, I'll stop. And we'll remove it out of there. I shouldn't do that. And its parent will adopt its subtree. Because they may have right children. So the iOS is the very smallest data in the right subtree. Very smallest is all the way left. We're going to learn how to do that first with a loop, and then we'll learn how to do that with recursion. But this will be next time. So bring your cameras. You will want to, now you've got the overview, you're going, okay, yeah. We're going to want